Welcome once again, and we are going to start talking about partial derivatives. It is about the derivatives, some kind of derivative of functions of two variables. Now, as we go on from here, the last part of this course, we expect a slightly more maturity from you and slightly more amount of concentration, because here the concept starts becoming different and maybe slightly difficult for immediate comprehension. You should not ever read science by thinking that science is all about absolute truths. Science is largely not about absolute truths, it is just creating some perception about the physical reality in which we are in, and mathematics is a tool which aids to that perfection. So, mathematics you cannot say is really a part of science, but mathematics is a language mixed with logic which aids in developing that perception of reality which we are trying to do through science. It is very important to have this view in the beginning. So, now when you have a function of two variables z is function of x and y. So, here you have two independent variables, now when we had function of one real variable, we had spoken about derivative with respect to that variable. So, how can I speak of derivative with respect to these two variables? This is something which is not so easily understood. There are a couple of ways of looking at it. I will not get into the deeper way of doing things, but I want to tell you that if I fix y, for example, in this function, then I have z to be a function of x only, and if I fix up the x, put some value say x equal to 3, then I have z to be a function of y only. So, if I take these two aspects of this function, then I can obviously use my standard idea of derivative and do it, and that leads to the notion of partial derivatives. Partial derivatives. So, when I am talking about partial derivatives at x, which I symbolize as del z del x, which is also written as del f del x, how do I define this? I define it same as the one I have known already, but what I do is I hold y constant. I think that it is a constant, a number, so I do not have to bother about its differentiation, right. So, its differentiation of that with respect to x would be 0, of course. So, I only increase or I only make an increment in the x variable and keep the y variable fixed. And this gives me what is called my partial derivative with respect to x. Similarly, you can talk about a partial derivative with respect to y, and of course, you can have a function of more variables and you can go on, but we are just going to concentrate on the simplest ideas. And then when you do this, you hold the variable x to be constant and make an increment only in the variable y. So, f of x given x y plus h minus f of x y by h. Remember, this is nothing but taking the ordinary derivative, these two limits, because these limits are limits not of functions of two variables, but functions of one variable, because y is constant here. Now, if I want to compute the function of a 2 variable, let us take an example and let us compute it. So, an example which will show you some important thing, that del f del x and del f del y, there must be a feeling that okay, del f del x is just a function of x and del f del y is just a function of y, but no, both are functions of x and y. You are holding y fixed for that moment, but actually you can give whatever values of y you want, right. When you have computed the value of del f del x, you can keep on giving values whatever value of y you essentially want. So, the partial derivative here, this actually if you go by strict things, then this actually means the partial derivative of f with respect to x computed at the point x y. Okay. The word partial, because you are holding one of the things fixed. So, this and this are functions of x y, functions of the independent variables x y. Now, take for example, which I take it off straight from the book Thomas and Finney, sorry, Thomas's calculus. Unfortunately, Thomas and Finney both are dead. So, if you look at this function, my first job is to take del f del x. So, what do I mean by del f del x here? I am now looking at y as if y was fixed. Now, I am differentiating with respect to x, y you can think whatever 2, 3 whatever you in your mind. So, take derivative of x square, which is 2 of x. Now, y is constant, so 3 into y is the coefficient of x, so it is just 3y and the derivative of x is 1. This is a constant, so the derivative with respect is to x is 0 and minus 1 is obviously constant, derivative is 0. So, it is 2x plus 3y, and it you see it is again a function of independent variables x and y. Now, if I compute del f del y, then you would immediately realize that this would become 0 because this is now x is being held as constant, and then it will become 3x plus the derivative of y here 1, and this is anyway constant. So, it is 3x plus 1, but observe here that the del f del y is here in this case is a function of x, not even a function of y. So, you have to be slightly cautious about this. For example, if you want to find a slightly more complicated function, again I am taking it from the book, which is the standard text for this course. I am sure many of you can actually buy it, not all, but many surely. It is around 400 rupees I guess now when I bought it, but I guess it can be bought and should be kept as a treasure. So, if I want to find say del f del x here, how do I do it? Note here this is a very complex situation, because here you have x both here and in the function cos x y. So, it is a you have to treat it as a product of two functions. Y I am keeping it fixed, you can put cos 2x, does not matter, and then you replace wherever the 2 comes as y. So, basically it will become x, the derivative of x into cos x y minus x into the derivative of cos x y, which is sin x y, and then you have to take the derivative, the chain rule, this is a function say 2 of x. So, you have to take the derivative of that, so a y would come here up again. So, here it is you see a function of x and y, again I take del of del y. Now, this x is constant, it will remain. So, it is minus x sin x y, again derivative of this with x y with respect to y will again bring me an x. So, it will become minus x s square. So, you see in both these cases I have these both of them to be functions of x and y. Now, I come to a crucial issue, is the issue of chain rule, because what would happen if you have more than, if you have the functions x y been related to some other variable, say t or some xi eta, we will come to them. But let me answer you a very important question before I go. You might think that, okay, what happens if you have a function of one variable and if that function is differentiable, we have mentioned that such a function is always continuous. Any function of one variable which is differentiable must be continuous. I would ask you to find the proof from anywhere you want, but this is a very well known fact. What happens if I have a function whose real this partial derivatives exist? Will that mean the function is continuous? The answer surprisingly is not. Let me give an example. So, this is what I am going to say, partial derivatives and continuity, that is our feature, and then we will move to the issue related with the computing of derivatives, that is the chain rule. Partial derivatives and its associated equations called partial derivative equations rules physics and engineering and chemistry, whatever. Let us get into this very important issue. Now, take an example. Is equal to 0 when x y is not equal to 0, and when the product x y is 0, it is 1. The important part is that I want to figure it out, you to figure it out as an exercise, that f is not continuous at the origin. See, people who has difficulty with this problem can ask this question in the forum and my TAs will answer you back. And the last one, which is more interesting, that the partial derivatives with respect to x and y exists at 0, 0. And they are finite numbers. Del f del x and del f del y, this is called the del of, not ddx of f, but del x of f or del f del x. So, this symbol, the for partial derivative which we had been using, I have not mentioned, this is called the del symbol. This symbol is called the del symbol, symbol which is taken out of the delta symbol, it is called the del symbol. These exist at the origin. This is a key fact. So, what conditions you should have on the partial derivative so that they are, the function is also continuous at that point? Actually, they should be bounded by a number which is independent of x and y, that is the answer. So, okay, let us forget about that, and before going into the chain rule, let us make certain additional things. We will now introduce something called second order derivatives, second order partial derivatives. Now, you have del f del x as a function of x y and you have del f del y as a function of x y. Now, because del f del x is a function of x y, you can then take its partial derivative if possible with respect to x and then with respect to y. So, if you take its partial derivative with respect to x of del f del x, then you write it as del x of del f del x, and this is symbolically written as del 2 f del x 2. Similarly, you take the partial derivative with respect to y. So, this is called the mixed partial derivative when you have a combination of x and y in the derivative. So, this is symbolized as del 2 f del y del x. Similarly, from f, so it is a partial derivative with respect to x and partial derivative with respect to y. So, this is with respect to x and this is with respect to y, this is with respect to x and this is with respect to y. So, you have here del x, because our first derivative is taking a derivative with respect to x, del f del y, which we symbolize as and pronounce as del 2 f del x del y, and this one is del y of del f del y, that would symbolize as del 2 f del y 2. Now, if you observe that these two are almost similar looking, these two are almost similar looking things. If these two are very similar looking things, how do you do you feel that almost okay, this should be same, but in general it need not be same. You have that del 2 f. So, the question is, when are these two same? It is a very deep result actually in analysis or calculus. It says that if all of these variables, because now this is a function of x y, these are all these 4 different second order partial derivatives that you see are functions of x y, and then if each of them are continuous as functions of x y, then these two mixed derivatives del 2 f del y del x must equal del 2 f del x del y. And now, let us come to the last part of the talk, which is about chain rules. So, now we come to the chain rule. Now, suppose we have a function, say z is f of x y and x is a function of t and y is also a function of t. So, y is y t, I can write it h t g t, does not matter, just for simplicity I am writing this. Now, so ultimately z is a function of t, because if I put the actual functional formulation of x with respect to t in place of x and in place of y I put whatever functional formulation y has with respect to t, then the function of f, the z now becomes a function of t. So, essentially what is dz dt? So, I am asking this question. So, this would be as follows, the chain rule is del f del x dx dt. So, if there was only one variable, so then it would have become df dx dx dt. So, because here I have two variables, I would have to add the other part also, del f del y dt. This is the first simple chain rule. You can have simple examples of this. For example, if you have say f x y is equal to x square minus y square, then suppose x is given equal to sin t and y is given equal to e to the power t. So, give me a t, it is for example, it is the, so it is a particle moving on a plane and at every moment time t you are giving the positions of the particle. So, it is a problem of mechanics. Now, essentially what you are telling that dx dt and dy dt themselves represent the velocity of the particles. Right. So, of course, it is not so easy to give a physical meaning to what we are doing here at this moment, but you can easily calculate out df dt. So, I will this is df dx, dx dt plus del f del y dy dt. Now, del f del x you can figure out very simply, it is 2xy into dx dt is cos t plus del f del y here is x square minus 2y and del f del y dt is E t. Now, you see there are a mixture of functions of x, y and t. So, what you do? So, it is 2 e to the power t sin t cos t plus sin square t minus 2 e to the power t e to the power t, that is the derivative, that is df dt. Now, we are going to go to the second formulation. Second formulation means I have z is a function of x y, but then x is again a function of 2 more variables and y is again a function of 2 more variables. So, let me say z is a function of x y and I have x now as a function of 2 variable r and s and y is another function of 2 variables r and s, and now hence the whole z itself is a function of r and s. So, it is now a function of 2 variables. Now, I can now talk about del z del r and I can also talk about del z del s, and now I want to find what are these in using the data that I already have. So, this will give you del z del x and del x del r. So, you first differentiate with respect to x partial derivative and then differentiate x with respect to r. Similarly, you have to do for y. So, del z del y del r. Similarly, in this case you have del z del x, sorry del z del x del s and then plus del z del y into del y del s, that is the chain rule. So, you can take a simple example, say z is equal to x square plus y square. So, z is equal to f x y is equal to x square plus y square. Now, I have written that x here is say r minus s and y is equal to r plus s. Then what is del z del r? It is del z of del x, del z of del x is 2x into del x del r, which is 1, plus del z of del y, which is 2y, del y of del r, which is 1. So, it is 2x plus y, 2x plus 2y. Now, what is del z of del s? Del z of del s is, you have again you start with del z of del x of del x is again 2 of x and del x of del s is minus 1. Similarly, you have del z of del y, which is 2 of y as before, and what is del y del s? It is plus 1. So, it is 2y minus 2x, and that is simply the answer. Of course, you can write x and y in now terms of course, you now, but now I have to express this as a function of r s del z del r and del z also as a function, del z del s also as a function of r s. So, I will put down x as r minus s and y as r plus s, and this will become 4 r and this will become 4 s, that is it. So, these are simple examples which to illustrate the chain rule. So, I hope you have a fairly good working idea about what are these. Proving etc. is different thing, we are not going to get into that, but let us just get into just have a look at the working details and with the examples see how to work with it. Thank you, and we will talk about total derivative, the mean value theorem for partial derivatives or mean value theorem for functions of two variables in the next class, and also about directional derivatives.